This is question 3 of the 2020 Level 2 Waves exam. Right, question 3. There is a third pool with a wave machine. The pool has a deep and a shallow end. The wave machine generates waves with a period of 2.3 seconds. The speed of the waves in the deep end is 2.75. Calculate the wavelengths of the wave in the deep end. So you've got the wave equation, which says that V equals F lambda, so the frequency times the wavelength. You also have 1 over the frequency is equal to the period. Conversely, if you flip both of these sides, the frequency is equal to 1 over the period. In other words, we're going to substitute this in. So we're going to have, I will rearrange for the, we're going to try and find the wavelength. So we'll rearrange for the wavelength. So we're going to have lambda is equal to the velocity divided by the frequency. And then because the frequency is 1 over the period, we just have velocity times, maybe I'll do it, divided by bracket 1 over the period. For those that can't follow algebra easily, that's probably the easiest way to show it, which is the same as velocity times time. And you'll notice, oh, this seems really familiar. Distance equals velocity times time. What do you know? And that is going to be equal to, so we're going to have wavelength is equal to V times T, which is going to be equal, well, that should be capital T for this period, 2.75 times 2.3, and I hope I haven't sucked this up, 2.75 times 2.3, and that equals 6.32. But the lowest amount of SFs is 2 significant figures, so we're going to have 325 meters, and then we're going to have right down here lambda equals 6.3 meters, and I could put 2 SF. There you go. You don't have to put this 2 SF, but I mean, yeah, I've always, in most of my other videos, always rounded to the correct number, so I should probably stick with it. Right, the waves move from the deep end to the shallow end of the pool. Also, I should have had this in color, it frustrates me. But anyway, complete the figure to show the effect, change of depth on the appearance of the wavefronts. So, has it given it away in the question? Ooh. The wave machine generates the speed of the waves. Deep end is that. Oh, it hasn't. It's not the first exam I've ever come across that had. Right, cool. Waves travel slower in shallow water than they do in deep water. I mean, it's just something you got to memorize. But pretty much every exam I've ever come across have always given it away in the question. This time they haven't, which is neat, I suppose. So it means the waves will be closer together. There you go. And they should really be the same separation distance. So I'm ballparking it, because I mean, I sort of back myself to be able to get it sort of correct. There we go. I mean, that looks, I'll just measure it quickly. We've got a 1.6, it's 1.3. Yeah, it's definitely shallow. Maybe I should have made them like drastically closer together. I mean, I can do that too, actually. I should just split them in half. There you go. That'll make it easier on the examiner, because there's no way you actually know what what the change in speed is. You just know they slow down. There you go. Now it's super obvious that they slow down and get way closer together. Use your diagram to show, to describe and explain how the wavelength, amplitude, and frequency of the waves would be affected as they move from deep to shallow water. Wavelength, they get shorter, obviously. Amplitude, frequency of the wave stays the same because it's conservation of energy. Amplitude, I don't even know, I have to probably look that up. At a guess, I'd say the amplitude probably increases because you're going to have conservation of energy. I mean, it's going to be all squeezed together. But I mean, water's a terrible example. And I suppose the waves, if you think about it, waves at the beach, I mean, you go out and see the waves coming in when they break just before shore. They are slightly, it might be calm way further out. That's because the wavelength is way larger. So the amplitude looks really small as they come in. I mean, it gets shallower, so the waves become higher. I mean, that's the nature way to think about it. Physics way to think about it is way more complicated than that. Water waves are not easy. Right, so I said as the waves slow down in the shallow water, they get closer together. Thus, the wavelength decreases. As both velocity and wavelength decrease, frequency remains unchanged. I mean, that's a bit of a cop-out because, I mean, the frequency could, maybe the velocity decreases a whole heap, only wavelength decreases a little bit, and frequency decreases as well. The true answer is that it's energy conservation. But I mean, this is the answer most times I look for. I should already put both. Anyway, and then the last one, amplitude increases as the peaks are closer. This is the only answer I can think of. I mean, the answers in the actual answer scheme aren't that great. Amplitude increases as the peaks are closer together, thus the same amount of water occupies less space. Conservation of mass means got to go somewhere, so it goes up. That's how I'd assume it works. Yeah, water waves are tricky because there's so much going on, because you've got transverse waves, and then you've got longitudinal waves, the actual water waves. You've got transverse waves inside the water where you get like compression and refraction of the actual water molecules. Yeah, not that easy. Anyway, on one side of the pool there are two lights. On the other side of the pool there are two speakers. Describe and explain the difference by the waves emitted by the lights and the waves emitted by the speakers. You should include a comparison of the wave type, need for a medium, and the speed of the waves. This is just the differences between the waves. Sweet. So, I mean, the sound waves need a medium to travel through. They need air or water. They can travel through any old medium. Sound waves are just refraction of the molecules, just bouncing. The wave travels through the molecules, whether it's an air, fluid, or a gas, or fluids are gases and liquids. Lights, they can travel through a vacuum. And sound waves are longitudinal waves because they're compressions of the air molecules or matter molecules. Lights are transverse waves because that's how the electromagnetic waves work. And the speed of waves, well, speakers travel at the speed of sound, which is 300 meters per second. Light travels at the speed of light, which is, well, it's 343 for sound waves in standard atmospheric conditions. Light's 300 million miles per second. Yeah, 3 times 10 to the 8. Right, I'll pause it and write it out a little more concisely. Right, so I just said light waves do not need a medium, whereas sound waves do, either sound, liquid, or gas. Sound waves are compression waves, so they are longitudinal. Light is a transverse wave. That's just a fact. Light travels at 3 times 10 to the 8 meters per second. You sort of need to memorize that. Surely they would have given, possibly, yeah, they would have probably given this to you in the fact sheet, which is a lot faster than sound and air at 343 meters per second. Sound travels about 5,000. 5,000? Yeah, about 5,000 meters per second in solids. Oh, no, and like metals and stuff. Some solids it probably travels a lot slower. What have we got here? During a test of an evacuation siren, sound of constant frequency is emitted continuously from both speakers. Lifeguard walks along the pool opposite sides of the speakers. Use physics principles to justify what the lifeguard would hear. You should use an illustration to explain. You may use a diagram to illustrate your explanation. So I'll do the diagram first, and then I'll write up the answer after that. So I'll have, I'm going to put the speakers down the bottom so we can have a more spread out pattern. So we're going to have, call this speaker. That should be SPEA, and then we'll have another speaker, and then we'll sort of have the sound waves coming out from it, and then like so, and I'll just like that, and like that, and that's pretty much all I need. And then from the other one, this is going to be super messy, but hopefully not too messy. Oh, I just need to made that a little bit messy. I might do it backwards. Keep my eyes like that, and then I'll do. Oops, I should have used a compass, but I mean close enough. Right, so we have that should be straight out, but I mean, as you can see, I'm uber messy. I've got one line there, one line there, one line there. So these are going to be the antinodes. A. If I had a compass and I'd done that super neatly, I mean, it would have been a whole lot better. And then between them, where a trough, so you got the max amplitude, and then between the waves you have min amplitude, there'll be a node. So I'm going to do it with dotted lines. And then I'll have dotted lines like so, and then you're going to have dotted lines out here. And the pattern sort of spreads out. Okay, you can see I'm super messy. This should be dead center, but whatever. So A antinode, N is equal to node. So I just said, as the sound waves cross the pool, they spread out directly between and in front of the speakers. The sound waves travel the same distance to the lifeguard, they should be arriving in phase, constructively interfere, creating a loud spot. As a guard moves to the left, they approach a point where the difference in distance is half a wavelength, and they arrive out of phase, resulting in destructive interference, and the sound heard quieter than usual. It's not completely gone, but it's just quieter. This pattern of loud and quiet continues as a guard walks along the pool. So as a guard walks along the pool, he hears the sound waves going in and out of phase, and they go in and out of phase because a difference in distance between the speakers goes half a wavelength, full wavelength, half a wavelength, and when it's half a wavelength, it's destructive interference.